video is to go through another example of eliminating the xy term. And remember, we're not rotating the conic itself. We're just coming up with a new orientation of the axes, so that if we draw that in an oblique angle, right, finding that angle, if we draw the rotated axes, we'll get that axis to line up and be the line of symmetry. So, previous to this video, we should have already, learned, derived, and be familiar with three formulas. First is the formula to identify the angle itself, which is the cotangent of 2 theta, always equaling the expression a minus c over b. And remember, a is the coefficient in front of x squared, c is the coefficient in front of y squared, and b is the coefficient in front of the other quadratic term, xy. Once we identify the angle, remember, then we're going to apply the two translation formulas. X is equal to x hat cosine theta minus y hat sine theta. And then y is equal to x hat sine of theta plus y hat cosine of theta. So again, excuse me, previous to this video, we developed and proved those three formulas. So let's go ahead and look at this example 4. And the first thing we're going to do is evaluate this expression. Solve for this equation so we can figure out our angle. So 4 minus 1 over negative 4. So we get the cotangent of 2 theta is equal to negative 3/4. Now, because of the symmetry of conic sections, we're never going to rotate or need to be worried about rotating more than 180 degrees. So if our 2 theta is representing a range of values between 0 to 180, then half of it's going to be just 0 to 90. And so that's where this half angle quarter view is talking about. Since our rotations follow this, we only have to worry about the positive in terms of our plus or minus. So that's nice, right? One less thing to worry about. But outside of the context, obviously, if we're solving, then we would. But in this case, we don't. And so the reason I'm referencing that is because when you see that the cotangent of 2 theta is negative 3/4, we don't have to worry about quadrant 4. We know it's going to sit up here in quadrant 3. And there's negative 3. There's 4, one of my favorite triangles of all time, right? 3, 4, 5 triangle. So remember, that represents 2 theta. So we need half of that. And if we're not allowed to use a graphing calculator to figure out what that angle is, we need to be able to manipulate 2 theta into theta. And that's where those half angle formulas that I just showed up here come into play. Okay, so we know that the cosine of theta would equal the positive square root, remember only plus or minus, 1 plus cosine of 2 theta over 2. And remember, this is still considered a half angle because this angle here is half of what's in there, right? So it's still half angle. Okay, so, and then, sorry about that. Same thing with then, similar, I should say, sine of theta is half of 2 theta. So sine of theta will just need the positive root, and it's 1 minus cosine of 2 theta over 2. Okay, so and since this right here is 2 theta, we know cosine of 2 theta is negative 3/5 based on this picture right here. Cosine of 2 theta is negative 3/5. So that's what we're going to substitute into our formula. So we get the square root of 1 minus 3/5 because it's plus that negative over 2. Well, 1 minus 3/5 is 2/5. Divided by 2 is the square root of 1/5. That's a perfect square in the top. So that is 1 over root 5. So cosine theta is 1 over root 5. And then sine of theta, so it's 1 minus a negative 3/5. So it's 1 plus 3/5 divided by 2. So that's 8/5 divided by 2 is the root of 4/5, which is 2, and then over square root of 5. And I'm just going to leave these root 5s. That's okay. 100% fine. Okay, so we did a lot of groundwork, and really that's it, just groundwork. This is helpful, and this is helpful. And we knew that based on this formula right here. So all those things are into play. We can now do the algebra that is required for eliminating our xy term. Okay, so back up to our equation up here. So we need, again, thinking about what is it that we're doing. We are taking this equation and we're rewriting it without x and y's and translating them to x hat, y hats, or x primes, y primes, whatever. Oh, but wait, we're still not done. Oh my gosh, we did all that work and I completely forgot. We still haven't done the rotation formulas. Sir Brown, this is just not good. So let's make sure we apply x is equal to x hat cosine theta minus y hat sine theta, and y equals x hat sine theta plus y hat cosine theta. So now we say, okay, x is equal to, well, since cosine theta is 1 over root 5, I'm just going to put that in the front, 1 over root 5 x hat. And then sine is 2 over root 5, put that in front, y hat. And then this y becomes, again, sine, which is 2 over root 5 x hat plus 1 over root 5 y hat. Oh my gosh, I almost tried to do the problem without having these formulas. These are what we need, combining those two ideas. Okay, now I can substitute way up here this 4x squared minus 4xy plus y squared plus 5 root 5x plus 5 equals 0. Okay, so and here's a great challenge. You should stop the video and do it yourself, right? And then fast forward and see what you get. So I'm gonna say, okay, here's the pause, stop, do that. But then, obviously you can continue and see me simplify as well. And hopefully I don't make any mistakes. I'm probably sure I will. So here we go. 4. 1 over root 5 x hat minus 2 over root 5 y hat squared. And then minus 4xy, so 4. So x, 1 over root 5 x hat minus 2 over root 5 y hat times 2 over root 5 x hat plus 1 over root 5 y hat. So that's the 4x squared minus 4xy, now plus y squared. So plus 2 over root 5 x hat plus 1 over root 5 y hat squared. And then we have our linear terms. Can't forget about them. Plus 5 root 5 times 1 over root 5 x hat minus 2 over root 5 y hat plus 5 equals 0. Okay. So when you expand, and I'll try to show you maybe an efficient way to think about this. Let's start collecting where these terms are coming from, and I want to try to be efficient here. So let's start collecting the x hat squared terms. Where are we going to get x hat squared terms? Well, from this first lead here, we're going to square that out. And if I were to square that out, I get 1 over 5 x hat squared times the 4. So that's 4/5. And then I would get x hat squared here times this. So that's 2 over 5. Don't forget your negative 4. So that's negative 8 over 5. For some reason, this one is right. There it is. Okay. And then if I'm squaring this out here, I'm going to get 2 over 5 squared. So 2 over root 5 squared, I'm sorry, which is 4/5. So those 3 terms are the only places where I'm going to get x hat squared. Okay, let's do y hat squared. Where will those come from? I probably should have changed the colors previous to this, but that's okay. So y hat squared is going to come from here. That's 2 over root 5 squared. So that's 4/5. 4/5. Excuse me. And then times 4. So that's 16/5. And it is positive. And then y hat's negative 2 over root 5 times 1 over root 5. That's negative 2 over 5. So it's negative 2/5 times negative 4. So that's 8/5 in the positive. And then our last y hats are right there. 1 over root 5 squared, which is plus 1/5. Now, I'm going to move this a little bit closer. So then, remember, the whole point of this is to get rid of x hat, y hat. And, you could solve these in good faith, and sometimes I do that, that really this should net to be a change of 0. we're anticipating this to be 0. So it's probably worth your time just to verify that. But eventually you can kind of work on good faith and not say, hey, I did the angle right. The XY terms are canceling. So XY terms will come, you'll get 2 out of here, double that. So it's negative 2 over 5 doubled. So it's negative 4 over 5, but then you have this 4, so negative 16 over 5. And then middle terms, xy, so you get 1 over root 5 times 1 over root 5 is 1/5. And then here you get minus 4/5. So 1/5 minus 4/5 is negative 3/5 times negative 4, so it's positive 12/5. And then our last ones will be the middle terms over here. And again, that's 2 times 2/5, which is plus 4/5. And I'm already anticipating, thankfully, they do get to 0. So I knew that that would happen. Okay, and then let's go ahead and finish out the linear terms. Can't forget about them. Plus, the root 5s cancel initially, so we get a 5x hat. And then minus 10y hat plus 5 is equal to 0. Okay, so we knew this was canceling to 0 because this value right there adds up to 0, which is wonderful. That's what we wanted to happen. And actually, ironically, this also is 0. That's not always going to happen. And what's amazing is that since it did happen, we get 0 x hat squareds. When we only get one quadratic, what kind of conic section is that? One conic section is a parabola. So, like again, maybe on a first inspection, we would never have guessed that. But now in the new rotated axis, we've lost x squared. So it is a parabola, one quadratic. Okay, let's count how many y hat squareds we have. 25/5, so 5. So you have 5 of the y hat squareds. And then we have, I'm going to, it doesn't like, I'm going to say minus 10y next, just for fun, y hat. And then plus 5 plus 5x hat is equal to 0. Now, I see everything's divisible by 5, so let's just do that. That's a no-brainer. Y hat squared minus 2y hat plus 1 plus x hat is equal to 0. Now, I'm also noticing that this is a great example. This factors to y hat minus 1 squared, and then we can move the x over and say equals negative x hat. And, like if you get a little, I get it, it's kind of tedious to keep writing hats for these, but it just emphasizes it's in the rotated system. So in the rotated system, I know the vertex will be at 0, 1, right? X hat, y hat will be 0, 1. And since it's y squared equals negative x, it's going to be opening towards the left. And I'm not going to be as particular about, being real accurate with these, so to speak, but what we can do is at least get a sketch. Okay, so what we need to do is draw a rotated angle of theta. And you might say, well, wait a minute, Mr. Brown, we never never really knew what theta was. And that's true. But guess what we do know? We know that the cosine of theta, is 1 over root 5, and we know that the sine of theta is 2 over root 5. So if you actually draw out what that looks like as a theta, here's theta, cosine is 1 over root 5, sine is 2 over root 5. We can draw our oblique angle. It has a slope of 2 to 1. It's actually a really nice angle, right? Nice line, y equals 2x. Y equals 2x, right? A slope of 2 to 1 would create the perfect rotation. Or I should say would create the perfect axes. So I can still draw in theta is a slope of up 2 over 1. So this should be my new axes. This should be my x hat axis. And then this would be the y hat axis. Okay. y hat. And then, again, our center is at 0, 1. So x is 0, y is 1. And we open our parabola to the left. Okay, so there is our sketch, which is great, right? Okay, now, I would like to do another example, example 5, but here's the thing. I would say, try example 5 on your own, right? Don't watch me do it. You do it, and then come back and see the solution video, which I think I might just make in this video, which is fine. So, but that's my challenge to you. Okay, so here's our pause. I don't know how long you're going to pause it. Okay, but now the pause is over. Hopefully you're done. So let's take a look at solving this one. So again, we'll start with cotangent of 2 theta is equal to a minus c. So 11 minus 1 all over 10 root 3. So that's 10 over 10 root 3, which is 1 over root 3. So that seems to be a familiar ratio. If you have 1 over root 3 is a cotangent ratio. And remember, that's representing 2 theta. This is 2 theta. Well, that's a 60-degree angle. So if 2 theta is 60, then theta is going to be 30. So that's nice. So it's a little bit different than the last example. So here's theta, 1, 2, root 3. So theta equals 30 degrees. So that means if I rotate by 30 degrees on the axes, that's fantastic. I'll be able to come up with a way to eliminate the xy term. And what I forgot, almost forgot, in the last example is our rotation formulas, right? So don't forget about these. X hat sine of theta plus y hat cosine of theta. Okay, now we know 30 degrees. We can now substitute. So x is equal to, well, cosine of 30 is root 3 over 2. So I'm going to say root 3 over 2 x hat minus the sine, which is 1/2 y hat. And then over here, let's go ahead and say sine, which is 1/2 x hat, plus cosine. So cosine we said was root 3 over 2 y hat. Now, just curious, looking at this, any guesses what it is? I mean, the last one kind of surprised me as a parabola. Nothing about the starting equation screams parabola to me. So I'm curious what we think this one might be. Place your bet, right? Take your wagers here. Okay, so we have our transformation formulas. Again, these are the things that are important that we'll substitute in to our original equation up here. So let's do it. Let's go here. So 11 and then x squared. So that's root 3 over 2 x hat minus 1/2 y hat quantity squared, and then plus 10 root 3. Now, anytime you got a root 3, you should be suspicious, like, 30, 60, 90 triangle, right, which we know. Root 3 over 2 x hat minus 1/2 y hat times the y, which would be 1/2 x hat, plus root 3 over 2 y hat. And then plus y squared. So 1/2 x hat plus root 3 over 2 y hat, quantity squared, minus 4 is equal to 0. So we don't have any other linear terms. That's kind of nice. And much like the last example, we're just going to collect terms. So let's collect the x hat squareds. So where are we getting them from? Well, here, root 3 over 2 squared. So that's 3/4 times 11. So that's 33/4. And then we'll get some from here, root 3 over 2 times 1/2. So that's root 3 over 4. So we have root 3 over 4 times 10 root 3. So I'm just writing here so I can see that. So that's 30/4. So I'll leave it unsimplified. That's fine. And then squaring out this, plus 1/4. Now looking ahead, that's fantastic. That's 64/4, which is 16. So that's a good piece of mind there, right? 16 x hat squareds. Okay, let's go to y hat squareds. Plus how many y hat squareds? So where are they coming from? So we're squaring out this side. So that's 1/4 positive times 11. So 11/4. We have negative 1/2 and positive root 3 over 2. So that's negative root 3/4. So negative root 3/4 times that 10 root 3. So that's negative 30/4. And then right here's our last one, 3/4. So let's see, that is negative 19 plus 3, negative 16/4. Oh, that's another good sign, minus 4 y hat squared. Okay, now we should be verifying that the x hat, y hat terms cancel, right? So again, we're checking this. We could do it on good faith and it just, sleep soundly, maybe, hopefully, that they're 0. Let's double check. So we've got 2 of the negative root 3 over 4. So that's negative 2 root 3 over 4. And then times 11. So it's negative 22 root 3 over 4. Okay, here we get, let's see, root 3 over 2. So that's 3/4. And then minus 1/4. So that's 3/4 minus 4 is 2/4 times this 10 root 3. So that's plus 20 root 3 over 4. And then we'll have 2 of these middle numbers. So that's 2 of the root 3 over 4. So plus 2 root 3 over 4. And luckily, just like we said, it's 0, which is what we wanted to happen. And then don't forget you have your minus 4. So we'll go back into here, minus 4. From this spot right there equals 0. Okay, so on this example, I'm going to divide everything by 4 and set this 4 to the other side. So this becomes 4 x hat squared. This becomes minus y hat squared equals 1. And if you really wanted to write this, you could say x hat squared divided by 1/4, because we like to have it in that structure, minus y hat squared over 1 is equal to 1. And what is this? Hyperbola. So, and it's a hyperbola opening in the x hat direction, and our rotation is 30 degrees. So if you draw your xy axes, and then you draw a rotated axis that's been turned counterclockwise 30 degrees. There's 30. That gives you your x hat axes and then your y hat axes. Fantastic. It's a pretty picture. Now, this particular one in the x hat, y hat axes is centered at 0, 0. So again, it just needs to be a sketch. But if you remember, so your denominators are a squareds and b squareds. So if a squared is equal to 1/4, that means a is plus or minus 1/2. B squared is equal to 1, so b is 1. So we just, like, if this represents a unit in the directions, sorry, that's 1 unit, 1 unit. So I should do that better. So half in the x direction is here, here in the y. So we can draw our little rectangle to determine our asymptotes. Remember, asymptotes are formed by connecting the diagonals. It gets a little messy here. And then we're opening in the x direction. So pick this nice blue. So we're opening, I should say, in the x hat direction. So just like that. Fantastic. Okay. Yeah, so there's our graph. All right, excellent. Now, I just want to show something. I think I can do this. This equation, 11x squared. Well, I'll do it in the next video. I just wanted to use Desmos to verify that. But this video has been long enough. So hopefully that you feel a little bit more comfortable with those 2 examples. And then there's going to be another video next about how do you tell what kind of conic section it is without having to go through this, right? Like looking at the equation, I wouldn't know that this equation that I'm looking at right now represents a hyperbola. The one before it represents a parabola. Like, how do you tell that? And the weird thing is that it all comes back to this idea of the discriminant. So that's the next video. We'll take a look.